Hello and welcome back everybody to geometry, and today we will be talking about the exterior angle theorem from section 7.3. Here is going to be kind of like what I'm going to be working at. Let me go ahead and give you kind of like a quick description as to what you're going to be seeing then. So the first part is we're going to define what is the exterior angle and also what is the remote interior angle. So there are two things that we need to define in this case. In addition to that, we're going to derive something called the exterior angle theorem, EAT for short. Yes, exactly. And then finally, we're going to look at a sample problem that deals with the exterior angle theorem and how do you actually use it so that that way we can actually do a proof. All right, so here we go. So in this picture on the bottom right here, you'll notice that I have a triangle ABC, and then there is an exterior point that we're going to go ahead and call D. That is going to be on the same line as one of the side, BC. So here is my setup then. In triangle ABC, if D is on BC such that C is going to be in between BD, then ACD is going to be the exterior angle. In addition to that, angle A and angle B are then its remote interior angles. So here in the picture, you can actually see that then. So angle ACD is located right here. And then that is going to be what is known as the exterior angle then. So you can see it's because it's outside. Now, the remote interior angles to that angle will then be angle A and angle B. Basically, the angles inside the triangle that are not next to the exterior angle. So that excludes C then. Okay, so that's how we define both of these terms. Now, here are some important notes about these two things. The first one is that for every two remote interior angle, there exists two exterior angles. Okay, so meaning that if I pick any two interior angles inside the triangle, there's going to be an exterior angle somewhere out there for it. Okay, there are two of the exterior angles. Well, wondering, okay, where's that second one coming from? Well, here, let me kind of draw the picture for you. Let's say, if you remember, that BC, I extended it so you can see where D is. But what if I extended AC over here and then created a point on that one, and we'll go ahead and call it E? You'll notice that BCE is also going to be considered an exterior angle. And those two exterior angles are the same because of vertical angle. And that's where the second one actually comes from then. So now you can see that angle B and angle A has two exterior angles over there, ACD and also BCE. And if I did the same on the other side, you can go ahead and see the other exterior angles as well. So that's where that idea came from. Okay, so next is that the second part is that there are 6 exterior angles for each triangle. And yeah, you can now kind of see all of those over here in action. So there are the first two, which are located over here. Then there's this guy right here, this guy right here. And then finally this guy right here, and then this guy right here. And note that I really should have made a different a symbol for it because they are actually not all congruent to each other. So just be very careful. They're only congruent to their vertical angles respectively for the exterior angles. Now here is something that you might not we might not notice because this was not as obvious. Assuming that we know that you have any triangle, the sum of the interior angles is equal to 180 degrees. Now that's something that, again, we haven't talked about yet, but let's just say for the fact that we actually know that. Okay, let's say that we know somehow, somewhere down the line that those interior angles adds up to be 180 degrees. So in our picture, what I'm going to do is I'm going to go ahead and erase some of this stuff so you can see what I'm trying to refer to. So let's go ahead and give some names to some of these angles so then that way we can actually work with them a little bit better, okay? So the first one I'm going to go ahead and name is angle A, which I'm going to go ahead and call X. Then I'm going to have angle B right here, which I'm going to go call Y. And then this one is going to be Z right there. And the exterior angle right here, let's go ahead and call it A for the time being, right? According to what is the assumption in this case, then that means that X plus Y plus Z is equal to 180 degrees, right? Because we're just assuming right now that we actually know that fact. Well, another thing that's equal to 180 degrees would be Z plus A, because if you notice, they form a linear pair, hence they are supplement to each other, hence they are 180 degrees. So then that means that 180 is also equal to Z plus A. And since they're both equal to 180, we can set them equal to each other. So x plus y plus z is equal to z plus a. And if I take out the z from both parts, hey, lo and behold, that the sum of the interior angles is actually equal to its remote exterior angle. So that is going to be a theorem that's going to be somewhere down the line. Now, unfortunately, we cannot actually do the proof for right now, but that'll give you an idea as to where we're leading towards. But for the time being, I think we can work with something that will help us out in this chapter. Since each one of these, the sum is equal to a, then I can actually conclude that x is going to be less than a, and also y is also going to be less than a. This is what is known as the parts theorem, if you remember correctly, that any individual components, so long as they are positive, if you add them together, is equal to a certain number. So then that means one of the part must be smaller than the whole part then. So that's where this whole thing actually comes in. So that right there, that is actually our exterior angle theorem. So here we go. Let me go ahead and scroll down to show you what I'm talking about. So theorem 7.2, the exterior angle theorem. So let's go ahead and read together. The measurement of any exterior angle, right, CBD in this case, is going to be greater than any of its corresponding remote interior angle. So that means that CBD right here is supposed to be greater than angle C, and it's also greater than angle A, right? That's the exterior angle theorem. So as a restate, I wrote that down on the bottom. Let point D be in the exterior of the triangle such that B is going to be in between AD. Then what I want to do is I want to prove that exterior angle CBD is greater than A, and also the exterior angle is going to be greater than C. So that is going to be my theorem then. So here we go. Let's go ahead and look at the proof of that just to see how that works. And again, we're not going to go ahead and write it in statement and reason because this one is going to be pretty lengthy. So let's see if I can go ahead and describe it using the pictures that we have. So here is going to be something that I'm going to do to make things a little bit easier. Now, will you normally be able to see something like this? The answer is no, because it's not as obvious. So that's where I need to kind of guide you through the way. What I need to do is I need to introduce a point M as the midpoint of CB and F such that M is also the midpoint of AF. So what I'm doing is I'm basically using the midpoint theorem to introduce the midpoint of CB. And then in addition to that, I'm going to go ahead and use the point plot theorem to introduce another point. We're going to go ahead and call F such that M is the midpoint of AF. So this is just in reference to the last section where we're going to introduce a whole bunch of stuff. Well, it's not really a whole bunch of stuff. It's just like two things. But here we go. First, I'm going to go ahead and draw M, which is the midpoint of CB. So there's that first part. Next, I am going to extend AM, right? So I'm going to go ahead and extend AM to as far as it takes so that the length of AM is congruent to the next part right here, which we're going to call F right there. Okay, so that is going to be my kind of like, rabbit out of the hat trick. All right, so now the question is, well, why do I want to introduce all that stuff? Well, let me introduce a few more items so then that way we can see how this proof actually works. I'm going to last introduce FB, which is this guy right here. Now, if you notice, the idea is, if you haven't figured it out yet, is I want to introduce some sort of congruent triangles to help us do this proof. And definitely from what we're seeing right there, yeah, we do have a congruent triangle, or we have a pair of congruent triangles. You can see that triangle ACM should be congruent to triangle BFM because of SAS. Looking at the marks right there, you can see why they are congruent to each other. So then that means by corresponding part, this angle C is then equal to this angle CBF then. Okay, so let me go ahead and write that down. Angle C is going to be equal to the measurement of CBF. Okay, so you're wondering, okay, well, what's so special about that? Well, look at CBF. That angle right there is a piece of our exterior angle that we're looking at, right? So the exterior angle, which is going to be CBD, is equal to the measurement of CBF plus the measurement of FBD. Okay, so that is using my angle addition postulate. And so if you're wondering, okay, well, what does that mean then to all of this? then that means that if I were to kind of like add on a piece of it, well, actually, let's make it substitution. Maybe you can kind of see it then. Here, since we say that the measurement of CBF is congruent to the measurement of angle C, according to CPCTC, we can go ahead and plug that into this guy right here. So the measurement of CBD is equal to the measurement of angle C plus the measurement of this FBD that's just like, floating out there. But right there, that's our parts theorem, right? Because look, if the sum of these two adds up to be equal to this thing, then that means the measurement of angle C has to be smaller than the measurement of CBD, which is the exterior angle. And there you go. That's going to be our proof. If you're wondering how we're going to prove the other part, measurement of angle A is smaller than angle measurement of CBD. Well, you just draw a same picture. Actually, not the same picture, but like the same. You're going to introduce a point somewhere else that is going to give you the same concept, and then therefore you're supposed to prove it again by parts theorem. Okay. All right. So this right here, I think there is something that we can do to make this a little bit more relevant. Okay, I think we can do something to make it a little bit more relevant. Imagine what happened once again in our picture, and let me go ahead and erase some of this stuff right here. What if I take CB? Okay, what if I take CB and rotated it so that it is right? It is going to form a right angle with AD. Okay, so imagine what would happen if CD wasn't like, this right here. Instead, let me go ahead and erase this part. Okay, so what if C is somewhere so that it is perpendicular to the line? So meaning like C is located over here. Okay, so what if I place C over there such that this is going to be perpendicular? Well, then according to this theorem, this exterior angle theorem, then we can actually conclude something very important over here. This angle is a right angle, and then outside the exterior angle CBD is also a right angle. This is going to be 90 degrees. So what that means is their remote interior angle, angle A and angle C, are going to be less than 90 degrees. So that is basically going to be that next corollary right here, which is kind of an extension of what we have. In any right triangle, the other two angles are, in a right triangle, the other two angles are going to be acute because of what I just said. You can say that the outside over here is going to be a right angle. Then using the exterior angle theorem, we can definitely then say that these two are going to be less than 90 then, right? All right, so here is a sample problem, just so that we can kind of use this exterior angle theorem to help us do some proofs. All right, so on the right-hand side right here, we're going to try to prove that the sum of any two angles inside a triangle is less than 180 degrees. You can see that our proofs, they're kind of like, scratching at that idea that, hey, the sum of the interior angles have to be equal to 180. But unfortunately, you're just going to have to, wait a little bit until that time actually comes. But for right now, we're just going to go ahead and kind of like, knock at the door and beat around the bush and see how we can get out of it. So there it is. As a restate, this is what I'm trying to prove. I'm trying to prove that A plus B has to be less than 180. B plus C has to be less than 180. And also C plus A has to be less than 180. Now, if I technically prove one, we can technically prove the other one because the proofs are exactly the same thing. So we don't have to do it 3 times, actually. We just have to pick one of them and, go with it. All right, so here is what I'm going to do then. I'm going to go ahead and write out on the right-hand side all the stuff that I can get out of the exterior angle theorem, right? So you can see how A, B, and C, those are going to be my interior angles. And then we have X, Y, and Z, they're going to be their exterior angles, respectively, okay? So the question is, well, how do I take what I have, right, which is here, according to the exterior angle theorem, to be able to build what I want that is over here, which is what I'm trying to prove. If you want to try it out for yourself first before I tell you the answer, feel free to do so. But if you're one of those that, want to jump straight into it, maybe we can go ahead and do that right now. All right, so here is going to be my proof then, okay? And it's one of those rare times that I'm going to go ahead and do a proof for you right in front. But, this one, I think it deserves it. So number one, what I'm going to do is I'm not going to actually use a given because there's really not much to be given in this case, right? Because it's already drawn there, what's exterior, what's interior, and so forth. But instead, I'm going to go ahead and pick one of these guys over here. Okay, doesn't really matter which one. The answer is no. I'm just going to pick one. So let's just go ahead and say that angle A is going to be, A has to be less than Y because of the exterior angle theorem. Okay, because you can see how A is the interior, remote interior angle, and then Y is going to be the exterior angle that's over there. All right, so remember what I said. I want to go ahead and build what I'm looking for, which is basically going to be one of these guys. Now, if you're thinking about tactics, which one am I going to choose? Well, I can choose the first one, or I can choose the third one because they both contain A. So let's just go ahead and take one of them and see what happens. I'm going to take the third one, for example. What I'm going to do is I'm going to go ahead and maybe I'm going to go ahead and add something to both sides. Maybe C in this case, right? Because that's how I'm supposed to build what I have. So A plus C is going to be less than Y plus C. And the answer for that one, or the reason for that, is supposed to be the addition property of inequality, because I'm adding something consistently from both sides to both sides with an inequality sign in between. Well, I built it, so that one's good. Now the question is, what is Y plus C? And if you look at where Y is located and where C is located, they form a linear pair. So then that means that that has to be equal to 180 degrees. So then we're going to go ahead and deal with that part. We're going to say that the angle, we're going to say that angle RSP and angle, I guess Y in this case, are going to be linear pairs, right? Because of the definition of linear pair. Okay, go through our normal motion. Then we can say that the angle RSP and angle Y are supplementary to each other. Okay, so that is going to be our supplement postulate. Okay, and finally, for the next one is now we're going to have to talk about their measurement. Technically, I'm not supposed to call it angle Y because Y is supposed to be a numerical value. I really should name that one, so that's kind of like my bad. So, just in case you're trying to wonder like if I messed up on the technicality, the answer is yes, I actually did that. So next, the measurement of RSP is supposed to be added with the measurement of Y, and that is equal to 180 degrees because of our definition of supplementary. And now, if you look at what I have right here in step 5, and if you look at what I have over here on step 2, this RSP is supposed to be, measurement of RSP is supposed to be C, so I can actually make that substitution to help you make it, to help you see it a little bit better. Step 6, what I'll do is I'll take step 5 and say that C plus Y is equal to 180 right there. And that is because of a substitution in step 5. And finally, if you look at step 5, look at step 6 and also look at step 2, we can make that substitution right there. So step 7 would be A plus C is going to be less than 180 degrees. And the reason for that is supposed to be the transitive property. Actually, no, I'm sorry. It's supposed to be a substitution in this case because transitive property, be very careful, has to deal with equality. So that